All right, good morning. Good morning. Hello. That was totally intended. That was exactly what I wanted to happen. So let me see. Okay, let's see how that works. So last time we started talking about the geometry of Gaussian distributions, multidimensional Gaussian distributions. And that is where we're going to continue today. So here's a reminder of something that you should know from linear algebra, but that we need to refresh for a moment. Make sure we're all on the same page here. So we're going to look at the eigenvalues of symmetric matrices. And the matrices that we're really interested in are covariance matrices. The covariance matrices specifically that parameterize Gaussians, or more generally, covariance matrices that we compute from data. Okay? So, but we're going to back up for a bit and think about covariance matrices in general, or positive definite matrices in general. So what I've written out here is the eigenequation. So the definition of an eigenvector and an eigenvalue, right? So we have some matrix A, and it's a square matrix with d rows and d columns. And now we're going to look at a vector in that d-dimensional space, and we say that's going to be we call that an eigenvector if applying the matrix to it only scales it, right? If we have a vector that's some direction in space, and now we apply a matrix to it. A matrix is a linear map, so it can do various things to that vector. It can rotate it around the origin. It can change its length. And if we apply it to two vectors at the same time, then it might skew them with respect to each other, right? So if we look at a vector, and the only thing that happens to it if we apply the matrix is that it gets scaled by something, that its length changes, but its direction does not. Yeah, then we call it an eigenvector. And the factor by which its direction or by which its length changes is called the eigenvalue. Yeah? So, and there may be, in general, for a given matrix, there may be several directions for which that is the case. And if that, then for each of them, we get a separate value here. Yeah. And the collection of all of those values is called the spectrum. Yeah. So the spectrum is the collection of eigenvalues, the set of eigenvalues of the matrix. And that is why, so whenever you see any title in machine learning, any method that is called spectral, then it has something to do with the eigenvalues and eigenvectors, right? So in mathematics, a property is called spectral. Property of a matrix or a linear operator of a linear map, it's called spectral if you can express it completely through the eigenvalues and eigenvectors. Okay, now in general, for an arbitrary matrix, the eigenvalues are complex numbers. No worries, we don't need that here. Okay, but in general, they are complex numbers. And there is a particular class of matrices that has a really nice eigenstructure. And those are the symmetric matrices. So symmetric in the sense of self-adjoint. If you take the transpose of the matrix, as you flip it across its diagonal, you get the same matrix back. Yeah? So, and what that means is one implication of symmetry is that all the eigenvalues are real. Okay, and the eigenvectors too. So, and the eigenvectors on top of that are mutually orthogonal. So this is really important. Okay, if you have a symmetric matrix, then all the eigenvectors are orthogonal to each other. Yeah.
classic mathematics, and what's special about that matrix mathematics is that eigenvectors perform orthonormal.
So the eigenvectors don't need to be orthogonal in general. They don't need to be orthogonal, right? So the orthonormality, and they're not automatically orthonormal. They can have different lengths, because if you scale an eigenvector, right? So here, if you look at this equation, right? If I scale this eigenvector, say by 2 on both sides, it's still true, right? And so that doesn't, just the fact that it's an eigenvector doesn't make it normal in the sense that it's not normalized to length 1, okay? So they are orthogonal. That doesn't mean they're orthonormal, but we can normalize them so that we get an O and B. Sorry.
Eigenvectors with distinct eigenvalues.
Yeah, we're coming to that. Okay. So the second thing here to remark is, as you just said, is the eigenvectors in general. You can have 2 different eigenvectors, so 2 directions that have the same eigenvalue. Okay, so they don't need to be, the eigenvalues for 2 eigenvectors don't need to be distinct. And in that case, that is called, the space spanned by these 2 vectors is then called an eigenspace, right? So you have some linear subspace of your space that is spanned by eigenvectors that all have the same eigenvalue. So you basically have an eigenvalue that is associated with that subspace. Yeah. So, and then the number of linear independent the dimension of that subspace, the number of linearly independent eigenvectors that have the same eigenvalue is called the multiplicity of that eigenvalue. Okay. But if we have a symmetric matrix that has full rank, yeah, then we have exactly d linearly independent orthogonal eigenvectors. Yeah. Okay. So in general, the number of distinct eigendirections is the rank of that matrix. Yeah. And the eigenvectors, if the matrix is symmetric, they are pairwise orthogonal. That means we can normalize them to get an orthonormal basis, which we may or may not want to do. And the rank of the if the rank is full, then these orthogonal vectors form a basis of RD. Okay. So, and now we have, we can subdivide or categorize these matrices as follows. If we have, so if we look at the eigenvalues, we now know in this case that the eigenvalues are all real numbers, right? So we can clearly say they're larger or smaller than 0. If they're complex numbers, then they're elements, then we can plot them in the complex plane, but there's no total order because it's a 2-dimensional space, right? The complex plane is 2-dimensional. So, but in this case, they're all elements of the real line that has a total order, so we can compare them to 0 and say they're positive, they're negative, or they're 0. And if they're all positive, strictly positive, then the matrix is positive definite. If they're non-negative, then it's positive semi-definite. And then we have the same for negative. And then the matrix is called indefinite if we have some that are larger than 0, some that are smaller than 0. Yeah, that's another question.
So if the rank A is the eigenvectors, the remainder, they still have an eigenvalue.
So if the rank is smaller than the dimension, then the image of the matrix has a dimension that is smaller than D, right? So if you apply that matrix to every possible point in your space, you get some, it maps to some subspace.
Yeah, but my point was that, like, if you have some eigenvectors, non-zero eigenvectors, then the remainder of the rank is taken up by eigenvectors, by the kernel, which are eigenvectors.
That's right. Yeah.
Do you not consider those as eigendirection?
No, we do not. We do not. Right? So it's so maybe I didn't. Let me just check whether I wrote that out here or not. Okay. So thank you. I should change that. I should add that here on the slide. So that scalar should be non-zero. Okay? It should be non-zero. It can be positive, it can be negative, it can be complex, it should just not be 0. Yeah? Okay. So And now, so we come to this orthonormal basis. I do hope you all know what an orthonormal basis is, but I wrote it out again. So if we have a basis of our space, so V1 through Vd here are vectors in this d-dimensional space. That's called an orthonormal basis if the vectors all have length 1 and are mutually orthogonal, right? And another way of saying that is that we take their scalar products with each other pairwise, and two vectors of length 1 have scalar product 1 if they point in the same direction, and scalar product 0 if they're orthogonal to each other, right? And so we get this case distinction here. There's a question in the back, yeah. So for a matrix of rank D, we have at most D different distinct eigendirections. But the matrix could have not full rank, right? It might not be full rank. Yeah. Okay. So in that context, let me just, so let me add to this here. If we have a symmetric matrix, then one of the beautiful things about the eigenvalues is that we can read off whether it has full rank or not from the eigenvalues. If all the eigenvalues are distinct from 0, then the matrix has full rank, then it's invertible. Yeah, so this matrix is, a symmetric matrix is invertible if and only if all its eigenvalues are distinct from 0. They can be positive or negative. If they're all distinct from 0, then the matrix is invertible, otherwise it is not. Yeah. So that is true for all matrices, but here we can compare, right? Here we can compare to 0. So in general, if you have some direction in which the matrix, so because it's linear, right? The only way that a matrix cannot have full rank, so that the image cannot be the entire space, if it collapses out at least one direction, right? And in that direction, you get a 0. Yeah. Okay. So if we have an orthogonal, so if we have an orthonormal basis here and take the vectors of this basis, so those are D vectors of length D, if we write them into the columns of a matrix, we get a D by D matrix, right? And that matrix has a property that it's an orthogonal matrix, which means its inverse is exactly its transpose. We transpose it, that's the same as inverting it. Yeah. So that is equivalent to each other. So an orthogonal matrices are precisely the ones whose rows form an O and B, an orthonormal basis, or equivalently whose columns form an orthonormal basis. Yeah. So, and any two another way of characterizing orthogonal matrices is they are those matrices, they are those linear maps that map orthonormal bases to orthonormal bases. Okay, so if you have a coordinate system given by an orthonormal basis, and then you have another one also given by an orthonormal basis, then the transformation between these two coordinate systems is given by an orthogonal matrix, right? So, and the way we transform between two of these O and Bs is, so we have one orthonormal basis here and one orthonormal basis here. Then there is some orthogonal matrix O that maps between them. And that means we have, if we take some matrix A and represent it in this basis, I wrote this as A sub V here. So that is A represented in this basis. So think of the matrix here as a linear f of A, rather as a linear map. And we can represent that map in a given basis as a matrix. But if we take two different matrices, two different bases, then the same map is represented by two different matrices. So if we take the representation of A in this basis and the representation of the A in this basis, then the way we transform between these two matrices, we get one of these matrices from the other, is that we take the orthogonal matrix O that represents the change of basis, and we multiply this matrix on one side by O minus 1 and on the other side by O. Okay. So if we put all that together, then we know that if we have a symmetric matrix of full rank, the eigenvectors of that matrix gives an orthonormal basis. if we have another symmetric matrix of full rank, then that also gives us an orthonormal base of eigenvectors. And we can transform between these two bases by an orthogonal matrix, right? Or if we just take one matrix and look at its eigensystem, so symmetric matrix of full rank, look at its basis of eigenvectors, and we take the standard basis, the standard Cartesian basis, we can also transform between these two by an orthonormal basis, yeah? by an orthogonal matrix. Okay. So now let's say A is symmetric. It has an O and B of eigenvectors, and the corresponding eigenvalues are lambda 1 through lambda d. Okay. So now, how does that matrix act on a vector? And the eigenbasis gives us a very nice way to represent what that matrix does to an arbitrary vector. Okay. So here's our arbitrary vector. We write that in the basis psi1 is to psi d in the eigenvector basis. Okay. So that means we have that vector that gets expanded in the basis. So it's the sum of the basis elements, and each basis element is multiplied by some scalar value, right? This is how you represent a vector. So these scalar values would be, if you write the vector as like the usual vector form as a list with respect to that basis, those would be the entries, right? So, and now we multiply that vector by our matrix A. What's going to happen? So we multiply A from the left to this vector. That vector is given by this sum over vectors, right? By this linear combination. So now, because A is a linear operation, we can pull it into the matrix, and we can pull it through the scaling here, right? So we get sum over these coefficients times A applied to each of the eigenvectors. But because we know that this is an eigenvector of A, this part here just amounts to scaling psi, right? So what comes out is this scaled form here. So that means a symmetric matrix acts by scaling along the directions of its eigenvectors. You can decompose the space into these directions that are characteristic of this matrix. And then along each of these directions, you only scale when you apply that matrix. Yeah. And it might not look like that because you're looking at it in the standard Cartesian basis, you're not looking at it in that basis. But once you change to that basis, you see that only scaling happens along each axis. There's another question there.
After I and lambda j, maybe equal to I and j distinct.
So yeah, you may have two different directions here in general, where you get the same two eigenvalues. Yeah. And we will see an example. So for instance, we will see that covariance matrices are of this form. And then the eigenvalues are exactly a type of are basically the variances. Yeah. And so two components could have the same variance. So, but for the moment, let's just focus on what happens here geometrically. Yeah. So if the matrix is symmetric and full rank, we have a basis of eigenvectors, right? An orthonormal basis of eigenvectors, right? So that means we can represent every vector in this form. We can retake any vector in our space and rewrite it in this form as an expansion in these eigenvectors.
So,
and then this comes out this way. Does that make sense?
Mm-hmm. So the eigenvectors forming a basis for RD, like for a full rank, general like full rank, this is not necessarily you may not have the eigenvectors forming a orthonormal basis.
Yeah, that's right.
You can look at like 1, 1, 0.
That's right. Yeah. So now let me try to illustrate what that means. Okay. That is, so this simple fact here is hiding behind a lot of things that are happening in machine learning and also in applied mathematics, numerical analysis, anywhere. Yeah? So here's an illustration of what happens. Here, let's just apply the same matrix multiple times to the same vector. Okay, so we start with some vector v, and now I apply the matrix to that once. I get av. Then I apply the matrix again to the vector that I got. So I have AAV, right? So, or that's A squared V, and so on and so forth. What is going to happen? So here, in the first example, this here is my vector V, and it's an eigenvector. Let's say this is an eigenvector, and it has eigenvalue 2. Okay? So I apply A once, then the direction doesn't change, but it gets stretched by a factor 2. Yeah? So I get this vector. Now I apply A again, it again gets stretched by a factor 2. Yeah? So direction doesn't change, but the length doubles with each application. Now in the second example, I take another vector. It's again an eigenvector, but let's say this time the eigenvalue is -1/2. Okay, so now two things are going to happen. One is the length doesn't increase, it decreases, but it also changes sign each time I apply, right? So the effect is, here's my vector, and the first time it gets cut in half and flipped, so I get this. Then it gets cut in half again and flipped, I get this, and so forth. Okay? So that's, yeah? No, this is just, we're going to look at a non-eigenvector on the next slide, right? But for now, it's just an eigenvector. So what happens if it's not an eigenvector, right? So if it's not an eigenvector, we're going to do our expansion here, right? So we're going to take V, we're going to expand it in this matrix, in this basis of eigenvectors. So these are its coefficients. And now if we apply a to the power of n, so if we apply a n times, then we can reapply the formula we've seen before. And the only thing that happens is that each time we collect a factor lambda j here for each eigenvector, right? So we get lambda j to the power of n. Yeah? So what does it mean? That means if we have the largest eigenvalue, right, then for that eigenvalue, this factor here is going to grow most quickly, right? So differences, relative differences between the eigenvalues are reinforced each time we apply a. Yeah? So here's an illustration of this. What I've plotted here is my vector v in black, okay? And the two blue vectors are the eigenvectors of my matrix. And I've scaled them according to the size of the eigenvalue. So here the eigenvalue is 1, and here it's, I think, 4. Or no, it must have a square root in there. Anyway, so here the eigenvalue is small, here it's large. So, and then I apply this matrix to this vector once here, and I get this vector, okay? So all I've done basically is I've taken this, basically what I've done is I've taken this vector and I projected it on this direction, I projected it on this direction, and then I scaled both of those components according to the eigenvalue, right? And on aggregate, because they are scaled differently, the effect seems to be that, or is that the vector turns, right? It changes direction, okay? So now I do that again, I get this vector here. And I do it again, I get this vector here, okay? So the most obvious thing that happens, well, it gets longer, but I could renormalize it. I could renormalize it and only look at how it changes direction, right? And how does it change direction? Well, you see that each time its direction becomes more closely aligned with the long eigenvector, right? So it slowly rotates towards the direction of the eigenvector with the largest eigenvalue. And why is that? Because the largest eigenvalue, relatively speaking, the largest eigenvalue overwhelms the others here. Yeah. So if you have an eigenvalue that is clearly larger than all the others, then you will see this effect if you repeatedly apply a matrix that things align towards that eigendirection dominates. And that effect is so important that this difference between the largest eigenvalue and all other eigenvalues has a name, and it's called the spectral gap. Yeah? So it's a vague concept. It doesn't have the spectral gap is, in principle, I mean, if you want to define it properly, it's the relative difference, the ratio between the largest eigenvalue and the second largest eigenvalue. but then people talk about it colloquially as, like they say, a matrix has a spectral gap if that difference is large, but it's not defined what large means, right? It's like kind of like, okay, that has a spectral gap. Yeah. Okay, but the principle here is the direction of a to the power n times v converges to the direction of the largest eigenvalue as this grows. Does that make sense? Okay. I mean, this idea is one of the most important things in this class, for sure. Not necessarily for this class, but like for life. Okay, believe me, it's. There's a question. Yeah. So, in the case of conjugate priors, we will see that this Gaussian geometry shows up if we have a Gaussian with a conjugate Gaussian prior. Yeah. So, and we will come to that later. Yeah. Okay. Actually, we haven't made it Gaussian geometry yet, right? We still have to do that. So far, it's just geometry. Okay. So now, if you in applications like Gaussians, for instance, symmetric matrices often occur in the shape of a quadratic form. So what that means is, very simply, you take the map from, so a quadratic form is a map from Rd to R, and it takes the scalar product of the vector of a vector with itself and inserts this matrix in between, right? So it's X transpose AX, if you will. Yeah? So on the previous slides, what we've done, we've just taken A and applied it to a vector. And now we're kind of basically squaring X. Yeah. So, and these quadratic forms are really if the matrix is symmetric, they're really the straightforward generalization of a parabola. Yeah. So this is a function on d-dimensional space that is real valued. Okay. And if you're in one dimension here, d is 1, then this is simply a quadratic function. Yeah? Simply a quadratic function. So in multiple dimensions, it looks, or in 2 dimensions, you can categorize these functions that you can get according to the eigenvalues. And they basically look like this. These are basically the 3 cases that we can see in 2 dimensions. So basically what happens is, if you look at this here, okay, this surface, this is like a bit of the function surface of a quadratic form. So here we have R2. R2 is down here in the plane, right? And then you have the surface above it. That is the value of this function. In this case, the function, if you would plot it larger, you would see something like a bowl shape. Yeah, so it's parabolic. Yeah, it's a bowl shape. And the reason is that this matrix here is, or in this case, this matrix is positive definite. Okay. In this case here, the matrix is negative definite. What you get is basically still a bowl shape, but now it's tipped over. Yeah, it's turned on its head. In this case here, you have 1 positive and 1 negative eigenvalue. It's indefinite. And what you see is that you get the saddle, right? So you have like something that looks like a parabola in one direction. And then in the orthogonal direction, you have an inverse parabola, right? So and that is why, I mean, if you see plots of saddle points in one dimension, it's not really clear why they're called a saddle point. They're called a saddle point because of this, because this looks like a saddle, right? Okay. So in this case here, the point here where the derivative is 0, that would be the saddle point. Okay. But these are basically really the only 3 cases that we see here. Either we have, so the matrix is 2 by 2. We have 2 eigenvalues. Either both of them are positive, both of them are negative, or one is positive and one is negative. If both of them are positive, we always get a parabola shape. If both of them are negative, we always get an upward down parabola. And if one is positive, one is negative, we get a saddle like this, right? And they may rotate and one direction may stretch. But basically what you can see happening here is that the behavior decomposes into 2 orthogonal directions. And we have 1 parabola along each direction. And we can tune that parabola individually by tuning the eigenvalue. Yeah. So here, both of them are positive. Here, both of them are negative. And here, one is positive and one is negative. But you can see that the way they interact with each other is really orthogonally. And that is because of the nice structure that we get, or the nice eigenstructure of symmetric matrices. Okay. So if we look at that in terms of contours, so here I've again taken one of these plots, in this case for this matrix here, and now I've plotted the contour lines of this, right? So these here are the contour lines. You can see, first of all, the contours are exactly elliptic, right? They're exactly elliptical. So, and then if I do that, then I can also plot in the eigenvectors. Yeah, and I've done that here again with the eigenvectors scaled according to the eigenvalue. So, and now you can see that these vectors exactly align with the directions of this ellipse, right? They're exactly aligned with the semi-axis of this ellipse. Yeah. So here in this case, dark colors are small values, right? So that is, here is the minimum, that is somewhere down here. And then there's a contour line here, and there's a contour line here, and so on and so forth. Yeah. And the red lines here represent the absolute values of the eigenvectors. Yeah, so and you can see that in the direction where the eigenvalue is large, the contour lines are closer together, so the function grows more rapidly in this direction. So large eigenvalue, large gradient. In this direction, it's smaller, so it grows less quickly. Yeah. Sorry, can you repeat that? The vector x that we put in that the function argument here. Okay, so the vector x, each point here in this square or each point on the plane is one possible value of x. And what I'm plotting here is the function value of the quadratic form at x. Yeah, okay, thanks for clarifying that. That's important. Yeah, what we see here are the function values of the quadratic form. At this point, this could be in point x, this could be a point x, and so on. Okay, so if we have strictly positive or strictly negative matrices, then we get elliptic quadratic forms. So these two are basically the same thing up to a complete sign flip, right? Okay, this is a case, you have done the same thing for a saddle point. So here we get contour lines that look like this, right? And that is something that you don't see immediately when you look at this maybe, but here along one of these lines, the value is exactly constant, right? And that is like, if you, once you know that, you can maybe imagine if you could draw a line somewhat like this way here, that you might get an actually exactly constant line. Yeah? So, and again, the intuition is that we have two exactly orthogonal parabolas that control the behavior of this shape. And if we flip the sign of one of the eigenvalues, and one of them flips upside down, and that gives us this shape. Yeah? So these kind of shapes are also called hyperbolic. Yeah. Okay, and this is an example of a saddle point in 2 dimensions. I just want to mention here, so if you, like these days, the way that saddle points come up in machine learning is typically that if you are in very high dimensions and you want to do optimization, then saddle points can be really problematic for your optimizer, okay? Why is that? That is basically, if you're in high dimensions, then, so imagine you locally approximate your function by a quadratic form like this, right? And that's basically what you do by computing the Hessian matrix. It's a local approximation by a quadratic form. So, and now you have a very high dimensional space that you decompose in many parabolas like this that are all orthogonal, nicely orthogonal to each other, but they can have very different scales. right? So you might have something along one direction here where the eigenvalue is very, very large and everything gets very, very steep. And you have a very small eigenvalue along a different direction. The problem with that is that when you do, if you do floating point arithmetic, that when you turn, your scale of resolution changes, right? You turn in space and your scale of resolution changes and might change by several orders of magnitude. And that just kills floating point arithmetic. Yeah, that's a really hard problem. Another one is that, and we're going to talk about that later, both of that later. This is just a remark for now. We're going to talk about that later in optimization. But another problem is that that gradient methods always like search in a specific direction, right? Here you just have to search in two different directions and explore the different behavior of this system. But if you have a billion directions here, that becomes a real work. Yeah. Okay. But that's just a remark for now. For now, we're really interested in Gaussians. Yeah. Okay. So now, Gaussians. So this slide is the exact copy of a slide that I've shown you before. But now we can look at it from a slightly different perspective. So we looked at the covariance, right? And the covariance was defined as this expectation here. So we take the two random variables, we center each of them by subtracting its mean, and then we take the product and take the expectation of that. The thing that I would ask you to note here, in this case, is that this is completely symmetric in 1 and 2, right? If I just relabel them, if I call this 2 and this 1, I get exactly the same thing back. Or if I swap 1 and 2 here in the arguments, I get the same value, right? Because it's just a product. Okay, so now the covariance matrix is what we got if we took d variables. And again, think of these variables as the entries of a vector, d entries of a d-dimensional vector. We take each of these entries is one scalar random variable, and we write the covariances, the pairwise covariances of these random variables into a table. And that's our covariance matrix. Yeah? Now you can see immediately, because this doesn't change if we flip the entries here, this matrix is symmetric, right? This value is the same as this value, right? And that's the same for every off-diagonal value, right? It's mirrored across the diagonal. So this is a symmetric matrix. And we now know that that means it has an interesting eigenstructure, right? So what is that eigenstructure? So that is what we're going to look at now. So let's say we have a Gaussian distribution and call its covariance matrix sigma, right? We know this matrix is symmetric. So we know there is an O and B consisting of eigenvectors. I'm going to call these eigenvectors xi1 through xi d. And again, I'm going to call the eigenvalues lambda 1 through lambda d. Okay. So what we now know is what this means. First of all, we defined Gaussian to be given by definition of the Gaussian, right? The covariance matrix is positive definite and strictly positive definite. So that means no eigenvalue is 0. It has full rank. Okay, it's a full rank matrix. So that means we have a proper O and B consisting of eigenvectors. And now we can take our coordinate system and change to the coordinate system consisting of the eigenvectors of the Gaussian, right? From the Cartesian system to the Gaussian coordinate system. And we know that that change of coordinates is given by an orthogonal matrix, because this is an O and B. And so that means up to some sign flips, maybe, it's basically a rotation. We basically take our coordinate system and rotate it into a Gaussian system. Yeah. So, and actually in this case, we don't have to do any sign flips because the eigenvalues are all positive. So it's actually a rotation. Yeah. We're taking our coordinate system, rotate it to this Gaussian coordinate system. So if we do that, then we know that the representation of this matrix in the new basis is diagonal, right? We haven't actually noted this yet. I mean, I think you know it, right? But I mean, what happens if we apply the matrix to a vector? It just gets scaled, yeah? So in the new representation, the matrix just consists of component-wise scaling, right? Dimension-wise scaling, and that is a diagonal matrix. So the diagonal entries are exactly the eigenvalues. So now the obvious question is, what are those vectors for the Gaussian, and what are those eigenvalues? What does it mean in terms of the Gaussian distribution? So here's again, here we again going to look at the quadratic form, right? And this is the quadratic form now that is given by the covariance matrix. So let's say my covariance matrix is the same matrix that I had before, right? This 2, 1, 1, 2 matrix. We saw previously that that has positive eigenvalues. So it's a legit covariance matrix for a Gaussian. I can just define the Gaussian distribution with that covariance matrix. And the eigenvalues, the eigenvectors are these two vectors that we had plotted before here. And here this is the same plot as before. These are the contour lines of this quadratic form as before that we had already looked at. So now what happens in the Gaussian density? In the Gaussian density parameterized by this, if I give it, so with mean 0, right? We don't really care about where we shift it. We just care about the shape. The shape is always the same, right? And then by changing the mean, we just shift it around. So let's just make it mean 0. We get a density that looks like this. Yeah, this is just the density given by this. Okay, fine. How do these connect to each other? Here I've plotted the contour lines of this density. Okay, so these are the contour lines of the quadratic form. These are contour lines of the density. If you compare them to each other, you see that they are related, but they're not the same, right? So basically what has happened is the ellipse has rotated by 90 degrees. And here the dark colors are in the middle and here they are at the rim, right? So this quadratic form here is, we've looked at that before, and it's bowl-shaped. So the minimum is in the middle, right? And for this density, I mean, obviously the density should be positive, right? And it's unimodal, it's a Gaussian. So the maximum is in the middle. Yeah. So that makes sense. And now what has happened here, what does this mean in terms of samples? That is something we already briefly looked at last time. If I look at these contour lines, right? Remember, if I then draw a sample from this Gaussian, then I get a cloud whose shape resembles these contour lines. We just want to figure out how exactly these contour lines and these relate to each other. Okay, so, and if we now think of these psi's we can also think of them as random variables, right? Because if I think of this covariance matrix as something that I compute from a sample of data, then the covariance matrix is actually random. And then these things become random variables. So what do they mean? Or alternatively, if you want to think about a fixed covariance matrix, just think of them as directions, right? What do these directions mean? So if we take our Cartesian orthonormal basis here, and then we can represent this matrix. We can represent each of these directions as some coefficients times the entries of the Cartesian basis, right? I mean, each of these eigenvectors here is just a vector in my space. Yeah. So the E1 through ED here are the standard coordinate vectors in the Cartesian system. Yeah. So the ones that have one entry that's 1 and 0 everywhere else. Yeah. So, and now that is the standard basis of my space. So each of these vectors here can be represented in that basis, right? And I can write that way. So another way of saying that is I think of this vector as a list, right? And I just take the entries of that list, and those are the values alpha I1, alpha I2, and so on. Yeah, so I can write that this way. So, and now I'm going to take these entries here and write them into a matrix. So what I've done is I've written my vectors into a matrix. So that's because the vectors form an orthonormal basis, that is an orthogonal matrix. Yeah. And now I can transform between the basis given by these vectors and the basis given by these vectors by multiplying by that matrix, right? So I get, if I take any vector x and represent it in this new basis, I get some new vector. So this is just a list with different numbers, but it represents the same vector. So now think of this x being the random vector that I draw for my Gaussian distribution. I'm going to take that random vector, I'm going to rewrite it in the basis given by my covariance matrix, and that gives me a new random vector here. And this is how the two are related, right? This formula defines this vector. Question? Sorry? Yeah, you can look at it that way, but I just don't want to get into that nomenclature here, right? Because we don't need anything else of it. We just need this relationship. Okay. Okay. So what do these directions, what is the meaning of these directions? So for any Gaussian distribution, we can first shift the origin. We can first take our coordinate system and shift the origin into the mean, right? So then we have a zero mean Gaussian. Okay. So let's say we have done that. And then we rotate the coordinate system into this eigenorthonormal basis. And then we write the covariance matrix in the new eigenbasis. The covariance matrix is a diagonal matrix. Okay. And in these coordinates, we now look at our vectors in these coordinates. So in these, if we rewrite our random vector in this eigen O and B, then that is a Gaussian vector, but the covariance matrix of this Gaussian vector in the new basis is now this diagonal matrix here. Okay. So we have changed the parameters of our Gaussian by rotating our coordinate system into it to align with its structure. Yeah. So now what do we know? We know this is a Gaussian with a diagonal covariance matrix. What does it mean? It means that the covariances of the different directions of the different x's are zero, right? All the off-diagonal entries are zero. So they're independent. If they're Gaussian, that means, and their covariance is zero, then that means they're independent. Yeah? So what we have done is we've obtained d new vectors, d new variables here that are mutually independent. They're just standard Gaussian variables up to scaling. Yeah. Okay. So what this means is that a multidimensional Gaussian, every multidimensional Gaussian, consists of independent orthogonal scalar normal variables, Gaussian variables, and the dependent in some coordinate system, in some orthonormal coordinate system, right? So we can always rotate our coordinate system to decouple things. Okay. And this is really something that is important to understand. If you use a Gaussian with dependence in it, then in a sense, that dependence is just an artifact of looking at it in the wrong coordinate system. Yeah? That does not mean we can neglect it. Okay? But you can get rid of the dependence by rotating into the coordinate system given by the Gaussian, and then it becomes just independent scalars. Okay, let's take our 5-minute break and then continue. Okay. So before I move on, any questions on what we've discussed so far? Any further questions on what we've discussed so far? Okay. So now, last time we briefly discussed maximum likelihood estimation. Now we're going to look at how to do maximum likelihood estimation in the Gaussian, the multivariate Gaussian. And for that, we're going to, as before in maximum likelihood estimation, we're going to consider a data set and data points. So each of these is now a d-dimensional vector, and I realize that I've just switched from a capital D to a small d here. My apologies. Yeah. So small d is now the dimension. So we have n d-dimensional vectors, and our model, our statistical model, remember a statistical model is a set of probability distributions. Our model is the set of all Gaussian distributions. I wrote G for Gaussian density here, with any mean in the space and any positive definite covariance matrices. So simply the set of all Gaussians that you can have on RD. Okay, so that is our modeling assumption. The distribution of the data is Gaussian. And now we want to do maximum likelihood estimation. And in maximum likelihood estimation for the Gaussian, we can treat the two parameters separately from each other. Basically, because of this property of the Gaussian that we can independently shift it around and scale it. Yeah, so none of the two parameters is a function of the other. Yeah? So we can treat them separately. And I'm just going to write theta for whatever the parameter is that we want to estimate right now. Okay, so when we're looking at estimating the mean and fix the covariance matrix, then theta is going to be the mean, and otherwise it's a covariance matrix. So in either case, our maximum likelihood ansatz that we discussed last time, right, is that we take the derivative of the log of the product and set it to 0, right? So remember, this here is the likelihood of the of one data point xi. Then we assume that the data are independent, identically distributed. So we get this product here over the joint distribution of the data points. The joint density is this product. Then we convinced ourselves last time that we can equivalently use the log of that product, right? And then differentiate, set that to 0. So if we do that, if we apply the log here, then we see that we get, so just take the log, pull it through, right? Then we get the sum of the logs of Gaussians, and then we apply the log to the Gaussian density, and we get this term here, right? So this here is a part that comes down from the exponential, and then this here is the constant up front, the density, the normalizing factor. Okay, so and now if you go through that and do the math, as they say, right, then you find that the two maximum likelihood estimators, so if you differentiate here with respect to mu, take that derivative, set it to 0, and solve for mu, then you find that the maximum likelihood estimator for the mean is just the normalized sum over the sample points. Yeah, so the sample average. And if you take sigma here instead, then you have to, I mean, it's a bit more work because the sigma, in the case when you're differentiating with respect to mu, this term just vanishes, right? If you're differentiating with respect to sigma, you have a sigma here too, you have to take care of that. But what you find is that the maximum likelihood estimator of the covariance matrix is the normalized sum over these products. So another way of putting that is this here is exactly the sample covariance matrix, right? It's, remember what we discussed last time with the law of large numbers, right? You can estimate an expectation by a sample average. If you take the function that gives you whose expectation you take in order to get the covariance matrix, right? The function inside the expectation. And for the outer expectation, you plug in the sample average, you get exactly this. Same here. Okay, so in these two cases, these are both cases where simply taking the statistic, and then plugging in, right? So writing the parameter as an expectation and then plugging in the sample average gives you exactly the maximum likelihood estimator. Yeah. And the reason for that is why that works here and for some other distributions, but not for all, is because here the parameters are chosen such that they are expectations of functions that we can compute. Yeah. Okay. So the result of this this coincidence, if you will, between the sample average and the maximum likelihood estimator is that the terminology, especially in machine learning, terminology sometimes confuses between the two, right? So you will see something that in context is really a sample mean, that then people refer to it as the maximum likelihood estimator. It is also that for the Gaussian, but you have to be a bit careful what it really represents in context. Yeah. That, of course, happens also with other things, right? The sample average, like other people, depending on which part of machine learning they come from, they will refer to the sample average as the Monte Carlo estimate or something like that, right? For reasons that we will see later if you're not familiar with it. Okay. Sorry? So we're not going to do the computation here because you're asked to do it. But what we do have here on the slides is a refresher for matrix derivatives, and we're not going to walk through this. This is not the kind of thing we want to walk through in class, right? It's just here on the slides as service, because if you haven't taken derivatives with respect to a vector or a matrix for a long time, then it might take some time to remember how that works. Okay, so we've just written out a few roots here on the slides on how to do that. Yeah. We're going to skip that here in class. So, but if you do that, then here's what you get, and here's what you get. Yeah. So now, so now we're going to talk about a brief example here, and that is a very simple form of linear regression. And I mean, of course, regression is ultimately what, like, if you use a feed-forward neural network, then in one way or another, you're doing regression usually, right? I mean, unless maybe you push a probability distribution through it. But in general, if you fit a function with a neural network, then you're doing some fancy form of regression. But here we're going to just talk about a very simple form of regression, where the regressor, so the function that you use to explain your data, is a linear function. But we're going to look at cases where it's not necessarily a one-dimensional linear function, but maybe a two- or three-dimensional linear function. Okay? So let's say our data looks like this. So this is the data. So these are the covariates in regression, not the responses. Okay? Put differently, our data set consists of vectors x1 through xn. So think of these as locations or arguments to the function that we want to estimate. And then y1 through yn are the responses. So those are the outputs of the function we want to estimate at these values, right? So the task here is find a function so that if I put in xi, I get out approximately yi for each of these data points. So each of these xi's is a vector in d dimensions, where I use d subscript x here for these vectors. And then each of the yi's also has some dimension, right? Same for all y's. And that dimension is dy. So these are two natural numbers here, right? And here in this case, these are our data points. So dx is 2. Yeah, and these are the two coordinates of each of the data. Each of these red dots here is one xi. Okay. So, and now we're going to look at a model that looks like this. What you see here is a Gaussian distribution, right? If you look at this, this is a Gaussian density. But you see that it's the random variable is the y here. And then here where the mean, where we would expect the mean, what we see is some matrix multiplied to x, and then we have a covariance matrix here. Okay. So, and let me try to explain where that comes from, like by a simple case in one dimension. I think that's easier to understand if we look at it in one dimension first. So here, x and y are both one-dimensional. X is on this axis and y is on this axis. So here, dx and dy are both 1. So the function that we want to find maps from the line to the line, right? So it's some one-dimensional function. And we assume that it's linear, which means it's a straight line. And it's specifically, it's linear, not affine. So it's in this case actually a straight line through the origin, right? Usually that's like the terminology is a little loose there. When you say linear regression, you really mean affine regression, right? It's allowed to not pass through the origin, but let's say it passes through the origin, okay? So, and here I've plotted a bunch of points. And basically, this distribution here, what it tells you in this case is if I have this line, how do I generate these points? Yeah. And the way you do that is you take this line, you take a particular location here, that is your x, your covariate x that is given. Now you compute the function value at that point, and then you add a little bit of Gaussian noise. Okay, so that is what we want to do in one dimension. So what do we do here? How do we do that? We get some value x, and then we have to compute a linear function, the value of a linear function at x. The value of a linear function at x is a matrix multiplied to x. So we take this x, we multiply it by a matrix. In this case, the matrix is just a scalar because we're in one dimension. Okay. So, and then that becomes the mean of a Gaussian. X times linear function of x. The matrix times x becomes the mean of a Gaussian, and that Gaussian has a covariance, or in this case, just a variance that tells us how far we scatter around. Okay. So if we now look at that in multiple dimensions, here's our function value. Here's our covariate value x. We multiply that by a matrix. So this operation here is compute the value of a linear function at x. And that becomes our mean. And then we scatter around that mean. We generate y by scattering around that mean with covariance matrix sigma y. Okay? Yeah. So in this case here, if x is two-dimensional, and let's say y is one-dimensional, right? Then what we would do here is the linear function would be a plane, a tilted plane, right? That is lives over the plane, like the canvas here would be R2, and then we would have a tilted plane function over that. Yeah. If D is 2, then I already don't know how to explain that. Yeah. Then we already have 4 dimensions in total, and we can't plot that. Does the setup make sense? Clear what we're doing here, what we're trying to do? I always take silence as acquiescence. So, so now, actually, let me. I don't want to be too confusing here, but let's just stare at this again. So, this is our model here. These values are given, right? And then, if we want to estimate the function, these values are given too. Right? And then when we want to do predictions, somebody gives us a new value x, and now we want to compute a y for that x, or draw a y at random. Okay? So now somebody gives us pairs of x and y, and now we have to determine the parameters of this model. Right? And the model is given by a Gaussian distribution. So now there's 2 ways that we could go about that. We could take a maximum likelihood approach, or we could take a Bayesian approach. Okay, and we're going to look at both of them. Maximum likelihood first. So, if we do maximum likelihood, then we want to maximize this function here, right? So this here is again our the model that we saw on the previous page, and now we substitute in our pairs of x and y. Then we go through the same thing as always, like take a product, apply the log, pull out the product through the log, so we get the sum here. Okay, so this is our data likelihood here. And now the unknown values here are W and sigma Y, okay? So, and let's say we make sigma Y, we make that variance here a model parameter. So we fix the scatter, make an assumption on the scatter. And the only thing that we want to determine is the W, which means that linear function, right? How much does that plane tilt, or that line, how tilted is it? So, and then that means we have to differentiate this expression now with respect to W and maximize. Yeah.
So even though this is maybe traditionally it's a supervised problem, you're kind of here treating it as an unsupervised problem by training. You're taking joint samples of X and Y, and then you know it doesn't matter that one is input and output here, it's just a joint distribution. You're using it for it to estimate W.
So the question is, like, are we treating this as an unsupervised problem here? I would say we're treating it as a supervised problem. We have response values, right? And these response values play a functionally different role than the covariates, right? Because we're like here, we're conditioning these values on the covariates. And then we assume that we can train that they can fit this model where we have both. So that is, I would call that a supervised approach. Yeah, only for inference. But yeah, supervision is always only for inference.
Right. Okay. So I guess all supervised problems will also do something like this, where it's just the stuff that's generating really just data.
Yeah. So yeah, okay. So to clarify, so in supervision, in supervised learning, the assumption that you have responses, that you have supervision information applies only to the training data, right? You always assume that once you've done training on new data, when you actually have to predict, you don't know what the right prediction is, right? So, okay, so here we have this. We're now taking the derivative of this expression here with respect to W. And then you just have to walk through these computations here, right? So they're a little cumbersome, and they look unpleasant if you haven't done this for a while, but they're also elementary, right? All you use here is basic vector calculus, right? And so basic linear algebra and taking derivatives, the few rules for taking derivatives with respect to vectors and matrices. So it's not that I assume that every one of you could just sit down and do that right away. But I hope you can convince yourself that, I hope you can believe that if you invest a bit of time and learn the right set of rules, then this is not super hard. Yeah. Okay. So, and now if you do that, then what you come out with is that this here is our estimate of W, right? And what we see here is a matrix where we take an outer product of each of these vectors with itself. Yeah. So, and then we sum that up over all our samples and take an inverse. Of course, if we take an inverse, we have to be sure that that matrix is actually invertible. Yeah. Now, there's a potential issue here, because if you just take the outer product of a vector with itself, that gives you a matrix. What is the rank of that matrix? 1, right? So it's 1. If you take d linearly independent vectors here and take these outer products and sum them up, then you get a matrix that has rank d. Okay. So if our space, the dimension of our space is d, and we have at least d samples, and if those samples are actually linearly independent vectors, then we get a full rank matrix here that we can invert. Yeah. So now we have to wonder, is that going to happen, right? Because now that becomes a stochastic question. When we draw vectors at random, what is the probability that they're going to be linearly independent? Now, it turns out if you draw these guys from a Gaussian distribution, say, and that Gaussian is not degenerate, so if it doesn't concentrate on some lower dimensional subspace, then the probability that they're going to be linearly independent, that any d up to d vectors that you draw are linearly independent, is 1. Okay, and that's not that hard to see, because in order for them not to be linearly independent, you would have to get several of them that are all on the same, all of them would have to fall on the same plane, right? Imagine some plane, like, so let's say we're in 3 dimensions. Imagine some 2-dimensional subspace. You would have to draw vectors from a Gaussian, and you would have to be able to draw 3 of them so that they fall exactly into the same plane, right? The probability of that is 0, unless you enforce it by making the Gaussian degenerate on that plane. Yeah. So in that is fine talking about that way when you're doing algebra. In algebra, something is either invertible or not, or it's either linearly independent or not. Okay. As soon as you do numerical analysis or statistical analysis, things become a little more blurry. Because imagine you have a Gaussian that is where this ellipse is very flat in 1 dimension, right? So one of the eigenvalues is positive, but it's tiny, right? So then to a computer that does finite precision arithmetic, it's going to look almost as if it's not invertible, right? So, and then you have randomness in there, and you might just draw a poor value, and it's really almost not invertible, right? So then you get big stability problems here. So what then happens is if you invert that matrix, right? If you invert a matrix, then you're taking the reciprocal, the eigenvector. So you take a symmetric matrix, you invert it. The eigenvectors of the inverted matrix, the eigenvalues of the inverted matrix are 1 over the eigenvalues of the original matrix. So if you have one that's very small, then now you end up with one that is very, very large. You apply that matrix to something, it's going to blow up that vector. Okay. So you can have this numerical phenomenon where something is technically speaking invertible, but it behaves almost as if it was not invertible. It just massively overemphasizes one direction. And typically that is where randomness really shows, right? You draw twice from that. It will blow up a direction completely different ways. Yeah, so it becomes very unstable. Okay, but if you draw sufficiently many points from a Gaussian that doesn't have one tiny eigenvalue, then this is going to be reasonably stable, this inversion. Okay. So just keep in mind that as soon as you're doing numerical analysis, or as soon as you're trying to estimate something, suddenly small eigenvalues can really matter. Yeah. I'm sorry. I'm getting ahead of myself. Questions on that?
Is there a general rule for how many samples you need in terms of the process?
So is there the question is there a general rule for how many samples you need here? There is not, because it depends, even for a Gaussian, it depends on the spectrum. It depends on, so if you invert a symmetric matrix, how stable that inversion is numerically depends on the ratio between the largest and the smallest eigenvector. It's also called the condition number. And if those are very far away from each other, then the inversion is unstable. And basically, with the geometry we've looked at, what that means is that the ellipse is very elongated, right? It's very long in one direction, very small in another direction. This is, again, exactly the same problem. So then for instance, you also get these gradient problems, right? You change direction with a gradient, and your numerical precision has to change drastically, right? So, and unfortunately, in statistics, where you often have to take products of things, you can get very different orders of magnitude very quickly, right? If you multiply up a bunch of values, right, then you can very easily, if you take a product of 10 values, can very quickly get to numbers of order of magnitude 10 to the minus 10, right? So you can really have cases where like it doesn't look so bad when I draw this matrix, this ellipse here, right, where we have like one eigenvalue is twice the other eigenvalue. We can see that it's elongated, but it's still plottable, right? If it's plottable, it's fine. That's like a good rule of thumb. But if you have a factor of 10 to the minus 10 between those two, then it really becomes problematic. Yeah. So you can give results on that for Gaussians, say, that then depend on the eigenvalues, but there's no general rule.
I think my question was, how does it depend on that?
Yeah. So if you want to know more about that, the best thing to look up, I think, is actually the numerics literature on condition of a matrix, right? And in numerical analysis, that same thing appears everywhere. So it appears for us in the context of samples and maximum likelihood estimation. So somebody asked the other day, I think, about the Fisher information matrix. The Fisher information matrix basically tells you how elongated this ellipse is. If the Fisher information matrix has a good condition number, then that ellipse looks roughly the same in all directions. In numerical analysis, that shows up every time you solve a linear system of equations, right? For instance, when you solve a partial differential equation and you discretize it, then the question is, how does your operator discretize and how stable is that under inversion? Yeah? So this same principle that we see here, the same geometric principle with this basis of eigenvectors, that just shows up everywhere in applied math and in machine learning and so on and so forth. As soon as you put math in a computer, you can't escape that. That's like fair to say, I think. Yeah? I mean, it's maybe a bit depressing that it's like 2023 and really all we can do is symmetric matrices in computers, but we can do quite a lot with it. So it's not so bad. Yeah. So now, there was one approach to solving it, right? Getting at the estimation, they're saying, okay, this is really an estimation problem or an inference problem. Is a Gaussian in there? We do maximum likelihood. Another one is to say we take a Bayesian approach and compute a posterior. So in this case, our matrix here, our solution is this matrix. Now we have to put a prior distribution on it, and of course we're going to use the conjugate prior. Okay, so if we assume that our response here is a scalar, and I'm just doing this for convenience, you will see it in a second. So let's say this is a scalar, then this matrix W is d by 1, so it's a vector. Okay, so all I have to do is choose a prior distribution on a vector, and I can make that a Gaussian. You know how to draw a Gaussian, a vector from a Gaussian, right? If we want this to be a multidimensional response, then W would be a genuine matrix. It would not just be a vector, and then we have to define a conjugate prior on a matrix. Okay, and we're just not going to do that to us here. Yeah, but there are different ways of putting distributions on matrices in this context, and two important ones are the so-called Wishart distribution and the matrix normal. Yeah, but so here, W is just going to be a Gaussian vector, and we're going to make it zero mean and give it some fixed covariance. Yeah. Okay, and then if we compute the log posterior, so now we have a posterior distribution on W. It depends on the data, right? So here we're conditioning on the data, and then it depends on this parameter we put in here and on the covariance of the data distribution, right, of the likelihood. So that was on the previous slide, that was a covariance matrix, capital sigma sub y, and now here this is just one-dimensional, so it just becomes the standard deviation. Yeah, so this is the standard deviation of the responses. So now we have this log here. So we look at this term. If we now write this posterior out in the base equation, then we have a product of two terms divided by something, right? So we have likelihood times prior divided by evidence, and the log is going to turn that into a sum, right? So we have log of the likelihood plus log of the prior minus log of the evidence. Okay. Now, I've grayed out a couple of things here, the A, the sigma, and this, because this term actually doesn't depend on A, right? It's just the data likelihood, and the A is a parameter of our prior. We didn't involve that in the definition of the likelihood. So that doesn't actually depend on this. Conversely, the prior doesn't actually depend on the data scatter. And then there is this term here, the evidence, and the evidence does not involve W at all, right? It's just a normalization factor in the base equation. And if we want to maximize something, right, or if we at least want to just do a proportional computation here, then we can just drop this term for now, okay? So then we take the log of this is a Gaussian, the log of this is a Gaussian, and so we get the quadratic forms that are in the exponent of the Gaussians. And then plus some constant, right? Some constant depending on the variances of these Gaussians. And then we rewrite that a little bit. We just collect terms here. And we're going to collect things into this matrix here, right? So here we get this contribution here, this A contribution, and then this contribution here from the x's. We're going to collect that up and write it like this, okay? So, and then we get these two expressions here, plus a constant. And then we can write that in this form, okay? So, and these two cancel out. So what we're left with is this here is, we again choose this as a proper normalization. We get the log of a normal distribution that is parameter, that has this mean and this covariance here. Yeah. So this here is a way to be clear. So this here, what we've done here is we've computed the posterior. This is now the log posterior of our data, right? And you can see the parameters depend on the data points. It's a Gaussian with parameters dependent on the data points. This is the conjugate update, right? We've just used the log in here for convenience in the computation. Pushed it through a log, computed what comes out, and then said, okay, this is the log of some distribution. That is our posterior, okay? So now it's up to us how we use that posterior. One way we can use it is we can do a map estimate, right? So that is something that we remember that we've discussed before. So there's like the one way of doing a parameter estimate is by optimizing the likelihood, maximizing the likelihood, we get the MLE. One thing is that we say we do Bayesian inference and we compute a posterior and then we work with that posterior. So there's not really a single value of the parameter that is our estimate. We maintain an entire distribution over the possible values of the parameter. And then there's kind of a go-between, which is the maximum a posteriori estimate, where we do a point estimate, but we derive it from the posterior by maximizing this posterior, okay? So, and if we do that, what happens? So the map is of that distribution is, so for W is this term here, okay? So this is literally just take this distribution here, okay, and pull out derive what the maximize it with respect to its argument. Sorry, I'm gonna go back again. Let me just. So this distribution here, this is written here as a normal, but if we write it out as a density function, then it's the density of W given these parameter values. And now we're maximizing it with respect to that W. Okay, we're just doing, we think of it as a function. We maximize that function with respect to W and ask where that is. So, and that maximum is at this point here, okay? And we can rewrite that as this. And the whole point of this exercise is compare this quantity here to the maximum likelihood estimate for W that we had computed on the previous slide, right? We had first looked at the maximum likelihood estimate and now at the posterior estimate. So the maximum likelihood estimate was this here, right? Here's again our inverse matrix inverted from the sample points, right? And then this term. Compare that to this here. This is the map estimate. What has changed? What has changed is only that this matrix here now has matrix A times sigma squared added to it. Okay? So the map estimate is the maximum likelihood estimate with a modification given by the prior parameter. Yeah. So, and now you can ask, is that a good idea, right? So we have this is our maximum likelihood estimate. Let's say we believe that the maximum likelihood estimate is in principle a good thing. So now we've basically taken the maximum likelihood estimate and we've distorted it, right? We're distorting the estimate. Is that a good idea? What is happening here is a form of regularization, okay? We're regularizing this estimate. And we just discussed a few slides ago that this matrix here can be very close to being singular, to being not invertible. Yeah? Can have a very small eigenvalue. So now what are we doing here? We're taking some matrix and add it to this. Let's say this matrix here is just the identity matrix that we choose our prior parameter here, sorry. Our prior parameter here is just the identity matrix, okay? Then what we're adding here is a diagonal matrix that has a constant value sigma squared on its diagonal, okay? So now if you take a symmetric matrix and you add a diagonal matrix to it, or you add the identity matrix to it, what happens to the eigenvalues? Does anybody happen to know what happens to the eigenvalues? Exactly. So if you add the identity matrix to a symmetric matrix and look at what happens to the eigenvalues, they each get a 1 added to it. More generally, if you take some constant tied the diagonal, then you just add that constant to each eigenvalue. It's also called a spectral shift, because you're taking the spectrum and you're just shifting the entire spectrum by a constant. Okay. So if you now imagine we have a problem here because one of these eigenvalues is absolutely tiny, right? Then what's happening here is we're shifting this eigenvalue away from 0. It's too close to 0. We're shifting it away from 0 by this constant here. Yeah. And so we're making the inversion of this matrix more stable. Okay. On the other hand, what we've done is we've distorted the value that we would get out by inversion, right? We've changed the matrix. So if we had a lot of samples, right, and think then in that case, this estimate would probably be a very good estimate, then we just want to run with it and use that. Because if we add something to it, then we're overruling the data, right? Effectively, we're modifying or we're masking the data. On the other hand, if we don't have a lot of samples, then this might save us from a bad estimate here, right? And this is an example of a bias variance trade-off. Yeah? So here, this term, if we have a few samples, this term has a high variance. If you think of this as a matrix that is random because the samples are random, right? If you would draw samples multiple times, and for each of these sample sets, compute this matrix. If each of the sample sets is too small, these matrices will tend to be quite different from each other. And then if you invert that, and one of the eigenvalues tends to be small, then you will get very different matrices as inverses that behave very different from each other, right? So between these matrices, you have a large variance, okay? By adding this term to it, you're stabilizing that inverse, and so you're reducing that variance. But at the same time, you're distorting your data, and so you're biasing your estimate, okay? So there's basically a spectrum there between large bias and large variance, and you have to decide where you want to be on that spectrum, right? If you have a large sample, if you really believe that you get a good estimate of this matrix, then you're fine not doing this, right? But if your sample is small, it might be beneficial to do that. Okay. So there is a specific terminology for that in statistics. If you do this spectral shift here, that is also referred to as shrinkage, which is one of these weird terminologies that if there are any statisticians here, I apologize for that remark, but there's one of these weird terminologies, nomenclatures that statistics sometimes come up with, that if you come, say, from numerical analysis, can be very counterintuitive because they often kind of start at the other end, right? It's just a different perspective on the world. So, but the idea here is that what it does is that it shrinks the weights of the inverse matrix towards 0, right? So if you invert the matrix, the weights can become very large. And by regularizing first, you prevent that from happening. And so you're shrinking them towards 0. Yeah. So that's why it's called shrinkage, even though in a sense, you're actually making something larger. Yeah? So, and this form of regression is also called, if you think of this as this estimate here, is exactly what in frequentist statistics or non-Bayesian statistics is called ridge regression. Yeah. So what you're doing here is you're taking this is what in regression is called the data matrix. You're taking that data matrix, you vector shifted, then inverted. That is called a ridge regression. Okay. Is that reasonably clear? Any questions on that? Okay. So the model that we've come up with here is a conditional model, right? So here we have modeled the responses conditionally on Y. So we're thinking of the relationship between these two not to be as functional relationship, but a stochastic relationship that we model by a probability distribution. So, okay. So here are a few reference pointers to various like write-ups and tutorials that are useful in this context. And what all of them have in common is that like they've been in here since long before my time. But I left them in here, even though they're a little dated, I left them in here because I think they're actually still useful. Yeah, because this material really hasn't changed. It's still in every model that we use somewhere, right? But a lot of this actually goes back to this fact that so many things in machine learning can be seen from a Gaussian perspective. That goes back to like some little paper that Zubin Garamani and Sam Robies wrote in the late 90s. And I think they just wrote it because they thought it was useful for them, and then they published it, and it had enormous impact in machine learning. Yeah, you won't see that if you look at the citation number, because in those days papers got much fewer way fewer citations than they get nowadays, right? So today you come at the right time for the right topic, you go home with 10,000 citations, even if nobody actually uses your paper, right? That was not the same back then, but it was really really influential because it pointed out something to people that they just didn't see. Yeah. So the crib sheet is, I think, is mostly about Gaussians, but I think it's useful for everything. Yeah. So then this one here is very specific to Gaussians. Sam passed away about 10 years ago, but NYU still maintains this page. Yeah. Okay, so now, everybody okay with that so far? So now we come to latent variable models, and this is like the first bit of latent variable models, but in some way or another, latent variable models are really the main topic of this module and the module afterwards. Yeah? So what we mean by a latent variable model is a model. So this here is something like a symbolic graphical model. I would call this a symbolic graphical model. Yeah. So it's a kind of a conceptual depiction of something like a graphical model. And the idea is that each of these nodes here represents a random variable. And you have conditional relationships between these random variables. And what a graphical model is going to be made much more precise in Manish's part of the class. Yeah, that is, the graphical models really provide a language for much of that class. But the idea here is as follows. The idea is that we have two types of random variables, and they're going to be denoted X and Z. Okay, so, and think of X as a variable that we observe. So something that that represents measurements of some sort that we want to explain, or data that we want to explain. Okay, and Z is a variable that is purely mathematical device. So this is just part of our model. It doesn't correspond to something we observe. It's an unobserved variable, and that is why it's called latent. Yeah, it is not latent as in not observed. Some people say hidden variables because they're not observed. But the principle behind it is that we can basically use simple distributions and combine them into much more powerful models by using these latent variables. Okay. So, and then you might have a structure like this where you have some of these variables here are observed, and then you're adding a model consisting of other variables and dependencies between them that are not observed. And then you work with that. Okay. So, and there's a general structure here with sampling things in layers. That is very common. So in almost all cases, or very many cases, these models have what is sometimes called a hierarchical structure. And what that means is you sample the generative process of your data is you sample a latent variable from some distribution. And then you use that latent variable to parameterize another distribution and sample from that. Okay, so you assume that your data is generated in 2 stages, or maybe more stages than that. First, draw some latent variable. That latent variable in some way determines the distribution from which you sample the data, and then you sample from that. Okay. So, and typically this is done in a way that you have no backwards dependence. So you draw Z without any information about X generatively, right? Of course, if you do inference, then that becomes dependent, but you draw that first without knowing anything about X, and then you draw X dependent on Z. And what that corresponds to in a model like this is that you have basically, you can group random variables into layers, and you have dependency only between layers, right? But they usually only go in one direction. And this is a principle that at a vague level is really very dominant in machine learning, not just in models that are probabilistic, right? If you think about a feed-forward neural network, in a feed-forward neural network, your variables are not random. They're just variables. The relationships between them are functional. There's some kind of link functions rather than distributions. But the magic that makes it work is that you group these variables into separate layers, and then you only have forward dependencies. And that's why you can backprop your way through them on, right? And here you have something like a probabilistic version of that structure, where you only have stochastic dependencies from one layer to the next. And again, that is what makes the computation work. And in both cases, you have the phenomenon that once you get loops in these dependencies, things become much more complicated. Yeah. So in a neural network, that might give you something like a ResNet. In graphical models, that leads to things like loopy belief propagation, right? But the general theme is using lots of variables and grouping them into layers. That's a good thing. Okay. That's like machine learning, modern machine learning in one sentence. Yeah. Okay. So there's different ways that you can interpret these latent variables, and don't think of these as the 3 categories. Just think of them as examples, right? There's like, I think there's probably, it's a philosophical question, I suppose, but there's not really a limited number of ways. Yeah. But one thing that you can do with them is you can use these latent variables to describe correlations between high-dimensional variables. Yeah, and that is something that we're going to see in dimension reduction, for instance. Yeah. They can capture a generative process. So you can think of the latent variable as some cause and as the thing that you observe as the effect, right? And that is used, for instance, that is one way to formalize causal inference, right? So if any of you are into causal inference, there's one view of causal inference that formulates that in terms of so-called DAGs, or directed acyclic graphs, right? That is exactly this point of view of the world, where you have a latent variable that causes something. And and then there's a way to think of it purely as an engineering device that allows you to put a distribution on some variable that you parameterize by a latent, make that, say, an exponential family model, then put another distribution on the latent that is, say, a conjugate prior, and then use a Bayes equation to compute your way through them. Yeah. Okay. So now let's look at a simple example of what you can do with a latent. And what you see here is an ellipse and a bunch of circles. Yeah, so there's an ellipse underneath here. And then there's a bunch of circles that are all exactly of the same width and aligned on some line here. Okay. So, and this ellipse, think of this ellipse here, and in each of these circles as the contour line of a Gaussian. So we have one Gaussian whose covariance matrix is some positive definite matrix that gives us this ellipse. And then we have a bunch of Gaussians whose covariance matrices have circular contour lines, spherical contour lines. So that means for each of these matrices here, the covariance matrix is diagonal with the same entry. It's just a multiple of the identity matrix, right? And what multiple gives us the scale of the ball? So, and the interpretation of this picture is it represents two ways of sampling the same distribution, okay? One way is we draw from this Gaussian here, and this is a Gaussian represented by this ellipse, okay? So it has mean 0. Again, we don't care about the mean. And it has this covariance matrix, okay? And so one way to sample a random variable x is to just draw from the Gaussian. So as we have seen before, if the ellipse looks like this, right, and we draw, say, 100 points from this, then we will get a cloud that will roughly have this shape, a shape reminiscent of that ellipse. Okay, so now here is a different way of drawing from the same Gaussian in two stages. So we first draw a scalar from a standard normal. Yeah, so this here is going to be a scalar value. And then we take that scalar value and we multiply the vector square root of 2 times 1, 1 by it. So this is a vector in this direction here, right? It points in the direction of the large semi-axis of that ellipse. So we randomly scale that vector by it. That gives us a point along this line here somewhere, right? And then we center a Gaussian at that point and draw with probability according to that Gaussian. So, and that Gaussian here has identity covariance matrix, and that's exactly the Gaussian represented by these circles. So each of these circles represents one instance of this Gaussian for one value of z. And by taking z randomly, I'm randomly shifting the Gaussian along that diagonal. Okay. So now if you were to do the computation, if you integrate this distribution here against this distribution, if you integrate out the z, then you would find that you get this distribution. Okay. And what that means is that if I do this two-stage sampling here, if I first draw z, that is now my scalar value, and then I draw x given z, then that is the same thing as just drawing x from the margin. Okay. So there's another important thing here to remember. Whenever you see, so what does marginalization mean, right? Or like if you take a marginal distribution and split it up into conditional times a marginal or prior distribution, that you can always think of that as a two-stage sampling process, right? So this kind of integral here, where you integrate out z, that is a way of saying I'm sampling z at random, then I'm drawing x conditionally on z and throw out z and just report the value of x. Yeah. So marginalization represents two-stage sampling. The other thing that I would want to clarify here is we've seen something like this before in Bayesian inference, where we drew a parameter value, and then we drew data given that parameter value, right? One important for a single data point, this two-stage sampling thing looks exactly the same. The math looks exactly the same. One important difference to keep in mind is in Bayesian inference, we draw the parameter value once, and then we draw all the data points given that one parameter value, right? We fix a parameter value, and then we sample condition on that parameter value. Here, we generate a separate latent for each of these data points, okay? So whenever you see a two-stage representation like that, try to figure out for yourself, like, do we draw from the first stage once and then fix it, or do we redraw each time? Yeah. Yeah, thank you. So I've just been kindly reminded I have to stop talking. I was just starting to enjoy myself. Too bad. There's one more question there. Is it quick, or should we take it to next time? Okay, so I think that bit is really important. So let's revisit it next time, if you can remind me. Okay, so thank you very much. See you on Thursday.